Alright. A curve in the xy plane is simple if it does not cross itself. So this is a simple curve, this is a simple curve. This is definitely not simple, and this is not simple. And a closed curve is a curve in which its initial point and its terminal point coincide. So this right here is not closed, but here, anywhere you pick, you could think of it as running a full loop and coming back. That's closed. This is not closed because those don't match. And this is closed because no matter where you start, you could think of running all around and coming back. So simple and closed have nothing to do with each other. Now I do want to talk about circulation and dispersion. So two things we're going to be measuring. We're going to be measuring flow, which is also known as circulation. So as you see, this right here is circulating. So here the flux will be 0. That's our next measure, the flux, which is, so here the flux is 0, and here the flow or circulation would be 0 because you're not circulating at all. This is just dispersion. So here you could figure out the flux, and here you could figure out what the rotation is. So two things that we measure, either rotation or flux. Flux is trying to figure out how much are you going to accumulate out of that vector field, right? Going out. Of course, not all vector fields look like this, but how much of that you're going to get. If you look at, Earth, everything is pointing inwards. The same idea, kind of like sun rays. If you want to figure out how much are you going to accumulate of the sun rays on a solar panel, for example, well, that depends how you really put out the solar panel, right? Do you put it this way? Do you put it perpendicular, depending on the time, and all of that stuff? Or think of it as water floating. This is like a source of water just bursting out in all directions. Well, there's no circulation. Everything's just being pushed out. Versus here, things are circulating. You're not going anywhere. You're not being pushed out or in. Well, we have two theorems, and we just need to separate between those. If R of t is a parametric equation representing a smooth curve C, which means you're going to use R to represent the parametric equation to represent the curve C in the domain of continuous vector field F, the flow, and the flow is also known as circulation. The flow is given by the integral along C of F dot T ds. Well, just to demonstrate, T runs the unit tangent. And if you think of this, since the unit tangent is actually r prime divided by the magnitude of r prime, if you remember, and isn't r magnitude of r prime ds? So if I write this as the integral along f, and if I replace this by r prime is the derivative of r once you have it, over ds, and if I multiply that by ds, well, those cancel out, and I'm left with the integral along c of f dot dr, and this should ring a bell because we talked about, where was it? Work. That's the same as work. So if I want to figure out circulation, that's the same as the integral of f dot dr. And if I want to calculate the flux across a smooth, it has to be a closed plane curve, right? The integral can be evaluated on any smooth parametric equation where they're saying given x and y, where x is a function of t, y is a function of t, t varies between those two values, that traces C counterclockwise. In case you've forgotten, that's positive rotation from trig, exactly once. So, given f, which is mn, the flux would be the integral of f crossed with dr. So I want circulation, I take the dot. I want flux, I cross. And you notice they're the same thing. That's the vector field, that's the derivative of that r. And this is the vector field, that's the derivative of that r. So, basically, given f to equal mn, and if I was given dr to be dx, dy, you know, these are a function of t, of course, all of them. When you substitute like we did in the last homework, right? If I want to figure out the flux, I would say that, and I didn't mention this right here, this small circular part indicate it's closed. The integral along the closed, so it has to be a closed curve of f crossed with dr. And in case you've forgotten how this works, you could make it 3D, you could make it 2D, mn and dx, dy. If you take the cross product of those, that is, I forgot to put that in there, of mdy minus ndx. And there it is. That's pretty much it. So, if I want flux, the cross product of f crossed with dr, and if I want the circulation, f dot dr, which is work. What's the catch? I need to figure out what f is in terms of t and what dr is, and pretty much that's it. Problem number 30 in the book says flux across a circle. Find the flux of the field, two fields, across this circle. Well, the flux is going to equal the flux along f1 plus I didn't. And did I forget to put it there? That'd be embarrassing. I didn't. Okay, very good. Well, let's see how this works. Well, r is given right there. So dr is really simple to find. That is negative a the sine of t for the I, and a the cosine of t for j. Okay, well, let's do this part. Let's label that blue. If I take f1 crossed with dr, and of course you could memorize that formula up there. And if I look at f, f is twice a cosine of t and negative 3a the sine of t, and copy that down there. That's negative twice a, no, that's negative a the sine of t and a the cosine of t. So that would be 2a squared the cosine squared of t minus, so plus 3a squared the sine squared of t. So here it's going to be the integral from 0 to 2 pi of twice a squared the cosine squared of t plus 3a squared the sine squared of t dt. Plus, I get to this piece. That's the integral from 0. Okay, color's not registering. Plus the integral from 0 to 2 pi. And if I take f2 crossed with dr, well, f2 is slightly different because f2, if I put that in there, that's twice the cosine of t. But if they put those two in there, that is a the cosine of t minus a the sine of t. dr doesn't change, it's right there. That's still negative a the sine of t and a the cosine of t. And that would be simply Did I forget an A? I did forget an A. That would be twice a squared the cosine squared of t minus, so a negative times a negative is a positive, a the sine of t times a the cosine of t minus a sine of t all dt. There it is. If on a test I say set up, do not solve, you would work it out and everybody's happy. Okay. On 31 through 34, find the circulation and the flux of the vector field F, there's the vector field F, around and across the closed semicircular. Again, it has to be closed for you to find the flux. Closed semicircle consistent of the semicircle followed by a line segment. Followed. These were not connected. No. Okay, here, my mistake. I'm sorry. Those are two separate problems. I didn't pay attention at all. I thought they were followed. So this is a problem by itself. That's a flux along F1, and this is the flux along F2. For some reason I thought the R's, there were two R's and one F. My mistake. Like this problem, it says you're gonna run across, we don't know what A is, so we don't know whether this opens above or below. It's either this upper half of a circle or this bottom half of a circle, followed by T. So it's a closed region, right? And here, of course, it was a circle running from 0 to 2 pi, so it's a closed region. Otherwise, you can't find flux. It has to enclose some area. So, how does this work? Well, let's do the circulation first. We know the circulation, well, it's going to be from negative A to negative B. So if I want the circulation, or flow if you want to call it, that's going to be the circulation along R1, or C1 I should say, plus the circulation along C2. Well, that's F dot dr, and that is F dot dr. Depending on the vector field, well, the vector field is really right there. And how does that work? Well, let's see. If I take the integral from negative A to positive A of F, what is F? Well, for C1, you're going to take this and throw it right there. That is A squared the cosine squared of t, and you're going to take this and throw it right there. That's going to be A squared the sine squared of t, dotted with, what's dr? In this case, if you take a derivative, that is negative A the sine of t, and A cosine of t, dt. So in this case, that would be the integral from negative A to positive A of negative A cubed, the cosine squared of t, sine of t, plus A cubed, the sine squared of t, cosine of t, dt. Alright, I'll get to that in a minute. Plus, along C2, well, C2 is really along that second vector. That's going to be negative A to positive. Oh my god, I'm messing things up big time. I'm sorry, guys. I'm not paying attention. I'm just too excited, I suppose. That's 0 to pi. I was going to say, how could they both have the same thing? And this negative A to positive A is only applying to this right there. Well, negative A to positive A of what? What would F be? Well, put the t in, t squared, and there is no j, so 0 squared. And what's the derivative of that? If you take dr, or r prime, that's 1, 0. So that's going to be t squared plus 0. And this cleans up just a bit. Let me see what that is. I could factor an a cubed cosine of t sine of t out, and I would have a negative cosine of t Or actually, I could just leave it like that. And I could let u equal cosine of t, du will be negative the sine of t dt, right there. And that will be the integral from 0 to pi. Actually, I could change the limits of the integral as well. I could say that's u squared. A cubed is just a constant. And that will be just simply u, so that's u squared over 2. Evaluated. If you put 0 in, you get a 1. If you put pi, you get a negative 1. And here, if you let u equal the sine of t, du is the cosine of t. Okay, I'm killing these problems. I'll tell you what. Let me work that out. If I let u equal the cosine of t, du is negative the sine of t dt. So that would be negative the integral from 0 to pi, and that's 0 to pi. I'm going to change that. If I put a u in there, that will be u squared, and this will be simply du. 0 in there, that's a 1, pi in there, that's a negative 1. Okay, that's pretty good. Plus, times a cubed, plus a cubed, and here if you let u equal the sine of t, du is the cosine of t dt. That works perfectly. So that is a cubed times the integral of u squared as well du. And here, if I let, oh, that's going to be a 0. If I put a sine, I'll get a 0, and pi, I'll get a 0. So this is gone. Okay, so my answer is negative a cubed times u cubed over 3 evaluated from 1 to negative 1. That's going to be negative 1/3. Let me get a bit more space. That's going to be negative a cubed over 3 into negative 1 minus 1. So that is 2a cubed over 3. There's still another piece. This piece right here, that is the integral from negative a to a of t squared dt. That is t cubed over 3 evaluated from negative a to a. That is 1/3 into a cubed minus a negative plus a cubed. So that is 2a cubed over 3. Oh, what do you know? They match. And we're going to add this. So the total circulation will be 4a cubed over 3. And if I run by the flux, now I'm going to copy this down one more time. Or I could set the flux on the right, I suppose. Oh, that's going to take some time. Okay, here. Okay. And I'm going to insert. So consider this 2 separate problems. That's all good. And that's still there. We want to do a bit more. Here we are. Let me erase all of that. We got the circulation. And if we want to get the flux, okay, that thing is like never going away. The flux again will be the integral along R1 or C1 of F crossed dr1 plus the integral along C2, and let's use a different color. Of F, that F crossed with dr2. Well, let's see how that works. Let's go on the side and figure out what is F crossed with dr1. That is a cosine of t. Nope. That is a squared cosine squared of t and a squared sine squared of t. And dr, if I take dr, the derivative of that would be negative a the sine of t and a the cosine of t. Oh, okay, that looks like this. I was going to say that looks very close. Okay, I thought I messed up on the previous. Okay, and what is that? That is a cubed the cosine cubed of t minus a negative plus a cubed the sine cubed of t. Okay, the first one we got. That's the integral from 0 to pi of a cubed cosine cubed of t plus a cubed the sine cubed of t dt. Very good. Plus, and if I take f crossed with dr2, well, that's going to be a bit faster because this is what we're using. So we put in for a t squared and a 0 because there is no j. And the derivative of that is actually 1, 0. So that would simply be 0. So if you work this out, you will get 4/3 a cubed. And that would be the final answer. On a test, when I say setup do not solve, I just want that part. I have one more to go. I want to find the flux. It says the vector field. Oh, come on. It says the vector field. Find the flux of the field F in exercise 35. That's it right there. Should make that look nicer. There we go. Okay, much better. Okay, and how does it work? Well, you want to run it across one zero, zero one, that direction. Negative 1 0. And back. So that's the direction that you have to worry about. Well, this is R1, R2, and R3. I gave you a line segment last time. That's why I separated those sections so you wouldn't have a hard time with this. What do we want? We want to find the flux. Well, the flux is going to be the flux along R1 plus the flux along R2 plus the flux along R3. So how hard is the problem? How quickly can you get R? R sub 1. You could use that formula that I gave you. Remember 1 minus t times the initial point plus R naught. You could say I'm going from 1 to 0 and 0 to 1. So I could say 1 minus t and let t vary between 0 and 1. If I put 0 in there, I am at 1, 0. If I put 1, I am at 0, 1. That works perfect. So in this case, I'm running from 0 to 1 of f crossed dr. Well, let's see what f is. In this case, f cross dr1. Oops, you guys forgive me, right? That is, well, 1 minus t plus t, right? That's f. That is 1. And 1 minus t squared plus t squared. That is 1 minus 2t squared plus t squared plus t squared. That is 2t squared minus 2t plus 1. And what's the derivative of that? dr. Derivative of that is negative 1, 1. So what would that be? That would be 1 minus that mess. Got the first one. So again, integration, assuming you could integrate. If I get to the second piece, well, I need to figure out what R2 is right there. R2, again, you could use the equation that I gave you, or you could say I'm going from 0 to negative 1. 0 to negative 1. And from 1 to 0. 1 to 0, that's easy. Let t start at 0, there you are. And from 0 to negative 1. So I could just say negative t. And have t varies between 0 and 1. If I put a 0 in there, I'll get 0, 1. And if I put a 1 in there, I'll get negative 1, 0. Perfect. That works. The integral, 0 to 1. What's the tough part? The tough part is figuring out f crossed with dr2. And in this case, let's see how that plays. Now, I'm going to take the sum of those, that's 1 minus 2t, and square that. Oh, there's a minus. I didn't see that minus. So that's a negative. So when you take this, oh wow. Yeah, I did subtract by mistake. Huh. So it's right. There's a negative there, so that's a negative. If I put a negative, that would be, let's see. So I'm trying to figure out what that is. Negative. If I put a that's t squared plus, if I square this, that is 1 minus 2t plus t squared. So that is a negative 2t squared plus 2t minus 1. Okay. And if I take a derivative of that, that's negative 1, negative 1. So what would that be? 1 minus 2t minus, because when you take this, those cancel out, minus 2t squared minus 2t plus 1, whatever that is. And I still have to do one more. I have to figure out what is f crossed with dr3. Well, what's r3? R3 is simply taking t0 and let t run from negative 1 to 1. That will work. That's going to be the integral. And let me shift this to the left a bit. It's going to be from negative 1 to 1, we said. Okay, now what? Well, here it is. t0. T plus 0 is t. And negative t squared plus 0 squared is t squared. And the derivative of that is 1, 0. So that's 0 minus a negative t, that's t squared dt. And there it is. That's the setup. And if you work this out, you will get the answer. And that's pretty much how much work is involved. 40 is the last example that I have. Well, find the circulation. What's the circulation? It's the integral along C of f dot dr of the vector field is given right there around each of the following path. I'm only picking B. So here, what is r of t? Well, you're circulating twice cosine of t, twice sine of t, and let t vary. Since you're getting the whole circle 0 to 2 pi, that will do the trick. So what do I need? I need to run 0 to 2 pi of, what's f? Well, there's the I. That goes for the x. That's right there. So that is twice the cosine of t, plus twice. And the y goes in two places. Twice the sine of t right there. Getting a bit excited. Plus twice that, oh, two times the sine of t, that is for the sine of t. Here we go. That is f. What's the derivative of this? Isn't that dotted with negative twice the sine of t and twice the cosine of t, dt? So that's going to be the integral 0 to 2 pi, and let's see what we get. We get negative 4 the sine of t plus 4 the cosine squared of t plus 8 the sine of t cosine of t dt. And that's pretty much it. You go from there and you figure it out. Well, you could simplify this just a bit. That is, you could say this is a negative 4 into 1 minus cosine squared of t. So that is a negative 4 plus 4 cosine of t plus 4. That's 8 cosine squared of t. And if you take a 4 out of this, you're left with twice sine of t cosine of t. That's sine of 2t. That you could integrate easily. This is negative 4. And you know how to do with this? Power reduction. Remember, this is cosine squared of t is 1 plus the cosine of 2t divided by 2. When you square it, you can simplify that a bit. And that will take care of this section.